start with an oral presentation in the session, then have 5 spotlights, and then another oral, and then 5 more spotlights. The first oral presentation will be presented by Pim Dahan on causal confusion in imitation learning by Pim Dahan, Dinesh Jayaraman, and Sergey Levin.
Hello. Hello, everyone. My name is Pim Dahan. I'm a PhD student at the University of Amsterdam and a researcher at Qualcomm. I'm going to present the work Causal Confusion in Imitation Learning, which is joint work I did with Dinesh Jayaraman and Sergey Levin while at UC Berkeley. Imitation learning is a powerful method of learning complex behaviors. It's used in practice for various complicated tasks, like driving cars, flying drones, or grasping fish. The simplest form of imitation learning is called behavioral cloning, and it reduces imitation learning to supervised learning and uses a data set of demonstrations containing observations of an expert and expert actions and learns a model, such as a neural network, to clone those actions. But it's not quite perfect. This is because when we have an expert in some state and an imitator that's learned to clone this expert, and we roll those out in the environment, we get that errors of the imitator accumulate, shifting it from states the expert encountered into new parts of the state space for which no demonstrations exist. This was noted in general, for example, by Ross et al. But we're looking in this paper at a particular form of distributional shift that arises by this phenomenon that is due to causality. Consider the following question. If we perform learning, does more information always lead to better performance? This is generally true for supervised learning, but what happens on a distributional shift? Consider the following hypothetical motivating example. We're going to do imitation learning to learn to drive a car. And in scenario A, our input consists of an image of the windshield, as well as of a dashboard that contains an indicator that says whether we are currently braking. In another scenario B, we block out the dashboard. And now we're going to do behavioral cloning to learn to drive this car. And we find that in both scenarios, we achieve good training losses as well as validation losses on held-out demonstrations of the expert. But what happens if we drive these on the road? It turns out that model B correctly learns to pay attention to the road and brakes whenever there's a person in front. But what happened in model A is that the learner learned to pay attention to the brake indicator, which lights up whenever we're braking, instead of the road view, and braking whenever the brake indicator is on, even though this is the effect of braking and not the cause. So we have a very surprising effect, that more information in the state here leads to worse generalization on the distributional shift. We see this as an instance of causal confusion in which cloned policies fail because they misidentify the causes that the expert pays attention to. Simplified, we have 2 random variables, the road view and the brake indicator, and want to predict the expert's next action. The expert only cares about the road view. This is the only cause. The brake indicator is ignored by the expert and a nuisance variable. However, we are in the Markov decision process, and the past state and action are a confounder, making the brake indicator still correlated with the expert's next action. This is because the past state in these kind of settings is often very predictive. The past action is very predictive of future actions. In general, if we have n state variables, we have 2 to the n possible. So if we learn an imitator, we can learn one imitator that pays attention only to the road view, just like the expert. Or we could learn an imitator that wrongly treats both variables as a cause. In general, if we have n such state variables, we have 2 to the n possible causal graphs. And only one of those corresponds to the causal graph that the expert pays attention to. In the rest of this talk, I will first show the existence of causal confusion and our experimental setup, then discuss our solution strategy, and show some results. So how might we demonstrate the existence of causal confusion? First, I showed a hypothetical example, but here's a real-life result from prior work by Wang in 2019. They do behavioral cloning to learn to drive a car in a photorealistic environment from GTA 5. They consider two setups, one in which the learner has access to history and one in which it doesn't. What they find is that on the validation score of held out demonstration data, adding history improves performance, but when driving on the road, it becomes much worse. This is very similar to our previous setup, where adding information leads to worse performance, so it shows that causal confusion is happening here. Similar effects have been noted in various other prior works. So how might we demonstrate this in a controlled setup? We take standard control experiments and add to the original state nuisance information to create a confounded state. The nuisance information we add is the past action. In our previous scenario B, correspond to just having the causal information, and we call this the original state, whereas our prior scenario A corresponds to the confounded state, as this brake indicator is present. So we do this for mountain car, as well as for Mujoko Hopper, and also would like to work with some visual states, for which we use the Atari simulator in the games Pong, Enduro, and Up and Down. Again, we want to add additional information about the past action. But instead of concatenating it, we here simply draw it on the screen. For our solution strategy, we would like to figure out causal graphs and want to have random variables that can be causes or not. To do this, we use a representation learning method and train a VAE to represent the frame into a latent dimension and treat a latent representation and treat the dimensions of those as potential causes. So now we do behavioral cloning, and we find that when we do behavioral cloning on the original state, we get quickly expert-like rewards after a small number of interventions. But on the confounded state, which has more information, we perform significantly worse, indicating causal confusion is clearly present. So how might we address this? What we need is to have a causal graph of the expert, indicating what are the random variables the expert pays attention to, as well as a neural network predictor to predict the action given these causes. We do this in two phases. In the first phase, we learn for all possible causal graph an optimal policy. And in the second phase, we're going to perform targeted intervention to infer what is the correct graph of the expert. Regarding the first phase, we can model all our possible causal graphs as binary vectors, with a 1 indicating a variable is a cause and a 0 indicating it is a nuisance variable and should be ignored. So now we're going to train a policy for all of these graphs, but we amortize that by learning them with a single neural network. For training, we do the following. We randomly sample a causal graph. Then we mask out parts of the nuisance part of the state by simply applying the graph as a mask on the state. Then we concatenate the graph also to the state and feed it into a neural network, which we use to predict the action. Then the neural network is trained with a behavioral cloning loss, and we learn our policies. So having learned all these policies, we now want to infer the correct causal graph corresponding to the expert. Expert observations are passive observations. And we know that in general, we can't always infer the correct causal structure from just passive observations alone. So we must intervene and change the distribution of state. We do this by executing the policies that we learned. Having done that, we're going to score all the possible graphs based on some additional information, for which we disambiguate two modes of operation. In the first mode, we assume that we have access to an expert that we can query on arbitrary states. In the mode 2, we assume we have access to some rewards in the environment. So as I said, we need to intervene to change our state distribution to score our graphs. But we can't, in general, just modify the state, for example, adding or removing a brake indicator. So what we do, but we are in a Markov decision process, so what we can do is change the past action, which in turn affects the distribution of state. This is an example of a generalized intervention on the state distribution. So in mode 1, we assume access to a reward which we can query on arbitrary states. This is similar to the dagger setup. For this, we first collect trajectories with the learned policies. Then we find the states on which all the graphs disagree most. We query the expert on those states, and we pick the graph that is most in agreement with the expert. Then we see that the upper bound of the performance of the result of this method is when we do behavioral cloning on the original state. The lower bound of the performance is when we do behavioral cloning on the confounded state. And we see that our method which observes the confounded state performs similar to the original state, indicating that a good causal graph is learned. A dagger baseline performs significantly worse and needs many more queries to the expert to achieve similar performance. In mode 2, we assume that instead we have access to some rewards in the environment. We do the following. We initialize a distribution over the causal graphs. Then we sample a graph from that distribution, and we execute the associated policy in the environment. Then we collect a reward with which we build a data set of graphs and rewards, and update our distribution over graphs such that graphs that get high rewards become more likely. We then repeat and pick the mode of this distribution as the result. Again, we have an upper bound of performance, which is the original state, a lower bound, which is the confounded state. A dropout baseline is used by Causal, doesn't perform much better than the confounded state. And our model, again, just as the first model, observes the confounded state, but performs similar to the original state, indicating that we infer a good causal graph. We can also visually look at the policies that we learn. If we learn a naive behavioral cloner on the confounded state, we see that our agent on the right mostly loses from its opponent. But the policy corresponding to our learned graph, again with the agent on the right, mostly beats its opponent and performs much better. But we can also look at the graph directly. We can also visualize the graph that we learn by doing the following. For a graph, we take a Atari Pong frame and we VAE encode it. And then for the latent dimensions corresponding to nuisance variables, we resample from the prior, the representation, and then decode. We do this a couple of times, and we see that only in the frame, only the nuisance digit corresponding to the past action varies, while the causal variables, the pedal and the ball, stay the same. If we would do this for a random graph, we see that all factors in the state can vary, indicating that our learned graph learns to only focus on the causes and forgets the nuisance variables. So to sum up, causal confusion naturally happens in imitation learning. And as a consequence, more information can hurt performance. We address this in our benchmark environments through targeted intervention. And how to scale this up to more complicated tasks is the direction for future work. If you would like to learn more, please come by our poster or visit this website. Thank you very much.
We have time for a couple questions, so if you have a question, please come up to the microphone, one of the microphones in the room, and ask your question. So I have a question. Would you recommend using your method for deployed imitation learning systems in industry right now? And if not, what are the limitations that you think need to be addressed before doing that?
That's a great question. So I think one of our main takeaways is that we should be aware of this phenomenon and should test our environments to see whether such nuisance information does exist and harms our performance. If you were to do such an analysis on your task and you see that there's some nuisance information, I think it would be wise to think of mitigation strategies to try to forget this nuisance information. I think our method is a good first start, but I wouldn't implement it in a self-driving car just yet.
If no one else has a question, I had one.
Okay.
Have you considered using this as an application, potentially the second method, as a way to learn sort of an interpretable causal graph for experts?
I haven't thought of that. So I think there are two cases to be disambiguated. Cases in which we have like an interpretable state and cases in which we don't. In our case, like in the mountain car in the hopper setting, we had some real state variables, and then we could interpret which of those are inferred to be causes and which are not. And I think that could be very insightful, where you really get some insight about what good behavior looks like. In the VAE case, it's a bit more murky as the latent dimensions don't have clear interpretations. But I think in the first case, it could very much be interesting. Thanks.
Thank you.
Yeah, I was wondering, another solution to this would be get more information from the teacher. Say you had an eye tracker and you knew where the teacher was looking when they were making these decisions. You could help use that information to help bias by supervising the attention as well as just what action is taken.
It's a good suggestion. Thank you.
Great. Let's move to the next speaker, and let's thank our oral speaker again. We will next have 5 spotlights, and you can come up. If you are a spotlight speaker in the next session and haven't checked in, please make sure that you're in the front row and come up shortly after the previous spotlight.
Okay. Hi, everyone. I'm Chao Yang from Tsinghua University. Here, I will give a short introduction about our work. Imitation learning from observations by minimizing inverse dynamics disagreement. We joined with Xiaojian Ma, Wenbing Huang, Fu Chunshun, Huaping Liu, Junzhou Huang, and Chuang Gan. First, imitation learning is a sequential decision problem, which can be considered as a Markov decision problem process without reward and an agent policy pi. Instead of using a reward function, we always give a set of expert demonstrations, which are the sequences of state action pairs. Throughout this work, we denote the joint distribution of state action rho pi SA and state transition rho pi SS prime. S prime is next step state. The goal of learning from demonstrations is to know an agent policy which can mimic expert behavior well. In this work, we consider a more spatial setting. Given the state-only demonstrations, how can we learn from the expert observations without action information? For example, if we give the robot a video about human pour water, how do we control robot to complete the same task? For such a robot learning problem, we would need less effort to collect demo samples, and maybe we can learn from internet videos. Furthermore, it would be biologically reasonable because human imitation never know what expert actions exactly are. From the divergence minimization perspective of imitation learning, we can see minimizing the F divergence between agent and expert could be a good solution for IL, such as GAL or GAL AIIL. The F divergence could be KL or GS divergence. And we can use some adversarial training for mechanism for divergence minimizations. Now we come back to the learning from observations. We can totally generalize to LF case. Due to absence of expert action information. So we can replace the rho SA with rho SS prime. However, can break the state transition distribution of agent expert sufficiently mimic expert behavior? In fact, not. We found a gap between those two methods, where GAL minus GALFO will equals inverse dynamics disagreement. We call this disagreement IDD. The IDD is the F divergence distance between the inverse dynamic model of agent expert. More importantly, IDD is an non-negative terms. So optimized GAL can optimize GALFO, but not vice versa. Well, certainly, IDD can sometimes equal to 0. If the dynamics model is an injector mapping, we can find GAL minus GALFO. So we can simply minimize rho SS prime in this case. As a general rule, we should minimize both IDD and GALFO terms. We can get our overall objective, which include minimize the GALFO terms and maximize policy interface and mutual information terms. From the TOEIC navigation examples, we can see our method, which considered the IDD issues, can be closer to GAL. Anti-gene tasks are compared with other LFO baselines, such as DP-mimic, behavioral clone from observations, and GALFOs. Our method can achieve the state-of-the-art performance. More examples and details can be found in our paper in supplementary. For more information, please come to our poster session 1 hour later. Thank you.
Hi, this is joint work with Chris Liu, Trevor Darrell, Philip Isola, and Alicia Fritz at UC Berkeley. How do we train a robot? Well, one way is to start training the robot for multiple tasks by showing it demonstrations, labels, examples, rewards, etc. But in this case, it works quite well for training, but the generalization to new tasks is very hard. The other approach, as argued by many, including Alan Turing 60 years ago, is to start the training of robot in a much simpler manner and let it explore and learn skills which are useful for many tasks. So in this case, while we want the robot software to start really simple, explore and learn skills, the hardware of this robot is still this complex piece of equipment. It has limbs and everything, right? So it's perhaps not quite reasonable to expect a big generalization by directly training from scratch on this complex hardware. So in this project, we wanted to go all the way back and start the hardware also from very simple stages. We were looking way back and looking for something really, really simple to bootstrap this learning process. And one such candidate for this evolutionary Big Bang sort of thing is this phase when single cells combine to become multiple cells. This is a phase when things go from all the time competition to collaboration. And they share objective and compose with each other. This compositionality has been very useful in language. But in language, the parser is usually fixed, so the task is a bit more tractable. Now, how do we implement this compositionality in hardware? And to investigate this direction, we designed this playground where we have this very simple, stupid limb, agents. These agents are basically a cylinder and a motor. They cannot do much, but they can combine with each other via magnet and become a new agent. And when they become a new agent, they share the reward and share the objective function, okay? Now, these agents are really stupid, and they only observe their local sensory input, and all they can do is apply torque, attach, or detach. Now, let's see one example task of this, the task of standing up. Now, in this case, if we apply a vanilla reinforcement learning, it works for 1 limb, 2 limb, and 3 limb. But as we keep increasing the size of the agent, the action space increases a lot, so that it fails to scale up. Now, in contrast, we allow these simple agents to self-assemble and become more complex on their own. Now, in this case, in the beginning of training, nothing happens. But after training, these agents learn to combine to become more complex. And the task in this case is to stand up. So they eventually learn to stand up. And it takes a while, but they can detach and attach their magnet. And OK, they stand up. Now, how do we learn these compositional controllers? Well, the main insight for us is to treat each limb as a separate policy network and share their parameters. But the key question here is that how to adapt when the agent changes, let's say from this shape to this shape, right? Our idea is to treat these neural net policies as Lego blocks. So we take this policy and we pass as input a message, let the policy modify the message and output something. These messages live in the same dimension. So you can really take an agent, have a corresponding policy, and when the agent limb changes from this one, let's say to here, you just cut the network from here and paste it here. The input of one network is the output of the other network. So you adapt by conditioning. So this is basically like graph network, but it's dynamic. So we call it dynamic graph networks. Now, all this that I described so far is basically like curriculum learning, but in hardware. Let us see some results. So how well does this generalize? Now, so in this case, I am showing the same policy I showed earlier, which was trained only for 6 limbs. Now, the same policy can work off the shelf for twice the number of limbs. It does not make a perfect tower anymore, because the task is much harder, but it does make a tower when there are only 4 agents or fewer limbs. You can also apply torque, forces, etc. The same policy, the same agent can still generalize without any further fine-tuning. Let's see one more task of locomotion. Now, it's the same setup. The task is to go to the right now. Earlier, it was maximize y-axis. Now, it maximizes x-axis. It makes these weird agents that can go forward. Now, these agents get generalized to new terrains as well, like these hurdles from that bumpy surface. One hypothesis for this generalization, without any further training, is that since the training is fully modular, a big agent for this hill is kind of similar to a smaller agent for small bumps. So the training being modular allows these agents to generalize seamlessly to these new environments. Now, since our agents are completely modular, they are also fine with losing a limb or two in between and still keep moving forward. Okay? Now, this might all sound a bit crazy and completely useless, which is kind of true, but there are actually some real-world self-assembling robots where this might have a potential use. And of course, the technique might be more general than the application. And this is work at UPenn, MIT, etc. If you want to know more about graph networks and these agents, come to our poster today. Thank you.
So hi everyone, my name is Nicolas Carion, and today I'm going to talk about generalization in cooperative multi-agent RL. So in this setting, we have a set of agents that must coordinate in order to solve a set of tasks. So sometimes several agents must coordinate in order to solve the same task, or depending on the scenario, they must also sometimes tackle the task they are best fit for. So we view coordination in RL as a dynamic assignment problem, which means that at each time step, a task must be assigned to each of these agents. We demonstrate this in this toy routing task, where the agents must pick up all the letters as quickly as possible, moving one cell at a time. The main contribution of our work is to find policies that generalize to more agents and tasks than seen during training. We use a neural network to compute scores for each pair of agents and tasks. Notice how the same neural network is used to compute the score of all the pairs. At test time, if we want to add more agents or tasks, it's really easy. It simply requires scoring more pairs. Once we have these scores, we use them to compute the assignment using a structured inference procedure that must also generalize to more agents and tasks. Once the agents get their assigned task, they use a fixed low-level policy to execute it. So in this toy example, the fixed low-level policy consists in going in the straight lines towards the assigned goal. We also replan at each step so that the agents that have completed their goals might be assigned to a new one. The baseline inference procedure consists in assigning each agent to its higher scoring task. So concretely, we look inside the set of assignment matrices for the matrix beta that maximizes these score functions, which is parameterized by the scores of the neural network. However, this strategy doesn't allow agents to coordinate very well. So in this example, only one agent is needed to pick up a letter, so it's wasteful for them to be assigned simultaneously to their closest task which happens to be the same for both of them. Instead, one of them should be assigned to the remote task on the left, even if they are farther away. So one way to increase collaboration between agents is to limit the number of agents that one can assign to a task, depending on their contribution to the task. So concretely, we had a linear constraint for each of the tasks, turning this optimization program into a linear program. The drawback of this approach is that it doesn't account for long-term performance implication. So in this example, only one agent is assigned to each task, but both agents happen to be assigned to tasks that are close to each other, while these tasks would have been best tackled consecutively by the same agents, while the other tackles the task on the left. So to better capture these long-term performance implications, we simply add a quadratic term to the objective function, effectively turning this linear program into a quadratic program. You can see on this example how it helps the agent spread optimally and solve perfectly this task. We now show some results in the challenging domain of StarCraft, where in these battle scenarios, our agents on the left must pick an enemy to attack on the enemy army, which is controlled by the built-in AI. So our strategy learns to focus its attack on a handful of units, and the constraints prevent the overcommitment. Strikingly, our policies manage to win 95% of the scenarios, even though the army is less powerful than the enemy's army. This policy also generalized to 5 times more agents than seen during training without any retraining. So as a conclusion, we showed a practical way to scale up multi-agent RL by training on small instances and then generalizing to bigger test scenarios. If you want to learn more about the model that we used and the way we trained them, I invite you to our poster number 194. Thank you very much.
Sorry? But I don't know how to go further because I tried to click, but maybe it's not the... Sorry? Why can't I go to the next slide? That's the clicker. Okay. Hi, I'm Thomas. I'm going to present a work made at InstaDeep in collaboration with the French National Center for Research, Paris-Sorbonne University, and Google DeepMind. In reinforcement learning, in most of the tasks, the most natural way to define a reward is to define as final and binary. In this case, you just tell the agent whether it managed to solve the task or failed. However, to learn something, the agent has first to find a reward, which can cause a severe exploration problems. So imagine that you want to sort a large list of numbers and that your actions are only swapping elements. In this case, if you just get a reward of 1 once the list is fully sorted and 0 otherwise, if the list is quite large, you may never find the reward by pure exploration. In this work, we propose to address this issue through recursion and a hierarchy of tasks, So what we do is that we divide, so what we do is that first, to run a main task, such as sort a large list of number, we divide it into subtasks that we run first and that then can be reused as actions to solve the larger problem. In this work, we define a task as a program, which is defined only through a specification, which is a test on the environment state. And then we define simply a reward, which is 1 if the program execution satisfied the specification and 0 otherwise. We tested our approach on 2 classes of problems. First, we try to sort a list of numbers, and then we try to solve the Tower of Funnel problem. We based on work on the NPI architecture that stands for Neural Programmers Interpreters, and augmented it to implement an actor-critic architecture. In the main strengths of the NPI architecture is to be able, into a single core interpreter network, to execute a whole set of programs and to reuse the programs that already been run to execute new programs. In the original work from Nando De Freitas and Scott Reed, this architecture was trained in a Fury supervised running setting. And what we propose to do in this work is to rather train it into a reinforcement learning setting, replacing the need for data by sparse reward. To deal with sparse reward and the credit assignment program, we chose to use AlphaZero as our agent to train the NPI architecture. So NPI works as standard program execution in a computer, which means that when a program wants to call another program, then it is saved into a stack. The other program's execution starts, and when it ends, the execution is passed back to the first programs. So to use AlphaZero with NPI, we had to enforce this mechanism into AlphaZero, and we had to augment it with recursion. So basically, inside the tree search, when the tree search wants to call a new program, the current tree search is saved into a stack, and the new tree search begins, and when it ends, the execution comes back to the previous tree search, which is depicted in the picture here. With this approach, we managed to solve both problems. First, we managed to sort large lists of numbers, and we trained our network only on a list of ranks 2 to 7, and then observed that it can generalize to sort lists of ranks up to 100. And we also trained it to solve the Tower of Funnel problems, and observed that only trained on 2 disks, it can generalize and sort and solve the puzzle with an arbitrary number of disks. We also observed, which was a very interesting finding of our paper, that as in AlphaGo 0, deploying the tree search at test time really helps. I will be glad to give you more details about this work at our poster. Thank you.
Hi, I'm Russell Mendonça. Today I'll be presenting guided meta-policy search. Reinforcement learning has enabled agents to acquire skills autonomously. However, the learning process can be quite slow. These plots show state-of-the-art deep RL methods taking about 1 million steps to learn on standard benchmark tasks, which corresponds to about 10 hours of train time on a real robot. Thus, learning from scratch repeatedly for large numbers of tasks can get very slow in terms of the number of samples required and also in terms of compute time. Meta-learning provides an elegant solution to this problem by effectively enabling agents to use their prior experience. This consists of a meta-train phase, during which an agent gathers experience, followed by a meta-test phase, where it quickly adapts to new previously unseen tasks. While current meta-RL methods can learn quickly on new tasks, they still face major challenges during the meta-train stage, where they gather experience. Current meta-RL methods require extremely large amounts of data to meta-train. These plots show current state-of-the-art on-policy meta-RL techniques requiring about 100 million time steps to learn on standard benchmark tasks. This corresponds to about a month of train time on a real robot. Furthermore, current methods face difficulty dealing with image observations and also with sparse reward due to the optimization and exploration challenges. It is important to address these issues before meta-learning can be deployed on real robot systems. We now proceed to discuss our method called Guided Meta Policy Search, or GMPS. We seek to learn a policy that can quickly adapt to solve any of the training tasks, as well as any new task, which is sampled from the training distribution. The key idea we use is to decouple the multitask meta-RL problem, to first learn local policies for each of the training tasks, which are then distilled to a single meta-learner in order to enable generalization to new tasks. Each of the local policies is learned using data-efficient reinforcement learning. We seek to learn a policy which, after a few, can solve any of the trained tasks effectively. In order to accomplish this, we train in order to match the action distribution of the updated policy to the action distribution of the local policy. This reduces to a supervised objective and corresponds to maximizing the likelihood of the local policy actions under the updated policy for each task. Thus, we have decoupled the multitask meta-RL problem to a single task RL problem followed by a multitask supervised learning problem. This enables us to solve much harder tasks due to the added stability of supervised learning. Furthermore, decoupling the problem enables us to use off-policy learning, and this yields much higher sample efficiency. For our experimental evaluation, we use 3 continuous control simulated domains: a sawyer robot which pushes blocks to different locations, a sawyer that opens the door to different target angles, and leg locomotion to various goal locations. We first compare sample efficiency against on-policy meta-RL methods. Here we have plotted average return against the number of samples required. We see our method has about an order of magnitude improvement over the others. Recent work has used amortized probabilistic inference to achieve data-efficient meta-reinforcement learning. While these methods get about similar sample efficiency to GMPS, we show much superior performance for extrapolation to out-of-distribution tasks. To illustrate this, consider the ant locomotion task. The green locations comprise the train set, and we test extrapolation to the out-of-distribution red target locations. While probabilistic inference struggles to generate useful context for such tasks, we are able to continuously adapt since we use gradient-based adaptation. We can also replace the local learners with user-provided demonstrations with minimal modifications to our learning algorithm. Here, we run the different meta-learning algorithms on sparse reward door opening and see that only our method is able to successfully meta-train since we leverage demonstrations to structure exploration. Moreover, we are also able to show effective meta-learning from raw visual input, since supervised learning is much more effective for optimizing convolutional neural networks. Thus, in summary, we decouple the meta-optimization objective, and thus we are able to achieve much better performance. I'd like to thank all of my collaborators. Please come visit our poster for more information. Thank you.
That was the last spotlight of our set of 5 spotlights, and we'll next start setting up for the next oral presentation. This oral presentation will be on using a logarithmic mapping to enable lower discount factors in reinforcement learning. The authors are Harm von Seijen, Mehdi Fatemi, and Arash Tavakoli. And at the end of this, this oral, we'll also have some time for questions. So if you have questions in the middle of the talk, please come up to the microphones at the end of the talk or shortly before the end of the talk in order to get your questions answered. Great, go ahead.
Hello everyone, my name is Harm van Seijen. The work I'm going to talk to you today about is joint work with Mehdi Fatemi and Arash Tavakoli. So let's get right to it. The setting we consider is the standard reinforcement learning setting. You have an agent interacting with an environment by taking actions at discrete time steps. Environment responds with an update of its state and update of the reward. So you can model this as a Markov decision process where you have S, a set of states, A set of actions, P, a transition function, R, a reward function, and S0, your initial state. And the behavior of the agent you can model as a policy, which is a mapping from states to actions. And the goal is to find an optimal policy pi star that maximizes some long-term objective. So that's a short summary of the standard RL setting. So now, what often happens in practice is that the way the performance is measured is different from the objective given to the agent. So a common combination is that the performance objective is the sum of rewards up to a certain horizon h, whereas the agent objective is a discounted sum of rewards, where the gamma here is called the discount factor that measures how future rewards are weighed with respect to immediate rewards. So in this setting, the discount factor acts as a hyperparameter, and a relevant question is, what's the best value of this hyperparameter? Now, if you play with this in practice, you're going to notice that most values don't work. It's especially if you use function approximation in sparse rewards domains. Actually, only values close to 1 work well. And so the focus of this talk is really trying to understand why this is the case and what can we do about it. So let's just consider a very simple task for a moment where we have a sequence of states. We have two terminal states, one leading to a reward of +1, the other to a reward of -1. We have some environment stochasticity, say with 25% probability. The action has the opposite effect of the intended effect. And so now the optimal policy for the discounted sum of rewards is actually independent of the discount factor for this particular task. It's always take the left action, very easy. So if you plot the performance as a function of the discount factor for the optimal policy, there's no difference. We can try to learn this policy now with reinforcement learning. If we use a simple tabular method, say Q-learning, you'll get something like this. So a performance of around 0.8 after 10,000 update sweeps. And notice that the performance is the same for any discount factors. Okay, now let's go to function approximation. And let's say we just do linear function approximation with tile coding with a tile width of 3, as you see over here. And if we now perform the same experiment, what you get is this. So for high discount factors, performance is okay, but performance drops dramatically if discount factors get lower. Now you can play a little bit with some settings. We can increase the tile width and double it in size. Actually, things get worse in that case. We can just throw a lot more samples at it. So let's give it 10 times more samples. What we see then is the following. High discount factors have now converged to the optimal policy, but still for these low discount factors, performance is terrible. So if you want to understand the reason behind this, we have to look at the action gap, which is defined in terms of the optimal Q value function. So let me define that first. So the Q star value of a state action pair SA is defined as the discounted sum of rewards if you take action A in state S and follow the optimal policy thereafter. Standard definition. So now the action gap is the difference, the action gap of a particular state is the difference in Q star value of the optimal action at that state and the best non-optimal action at that state. And the relevance of the action gap is that if you manage to bring your error on your Q-value estimates, if you can make it smaller than half the action gap for every state in your MDP, then you're guaranteed that your greedy policy is going to be optimal. So the action gap tells you something about how small your error should be if you want to be optimal. So let's have a look at how the action gap looks for a very simple problem. So another state sequence, an even simpler one than the one before. So we just have 50 states, 1 terminal states. And the action gap for this particular task is very simple. It's the Q star value of your left action minus the Q star value of your right action. So you can plot that, which I've done here. So the x-axis is the state index. So this shows the action gap across your state space for different values of your discount factor. And what you actually see is that the action gap exponentially decreases the further you get away from your positive reward. And exponentially decreases with a discount factor as the base, which means that if you have smaller discount factors, this effect it is going to decrease much more rapidly. So you can now, based on this graph, you can come up with a number of different hypotheses about the poor performance of low discount factors. So a very simple hypothesis is simply saying, okay, if my action gap gets too small somewhere in my state space, that messes up my optimization. You can actually very simply test this hypothesis, and it actually turns out not to be the case. And so for details of that, look at the paper. But we tested a number of hypotheses based on this graph, and we disproved most of them. But we also found one hypothesis that we were not able to disprove, and actually we found very strong evidence that this is the true cause of this bad behavior for low discount factors. So let me read it. So this hypothesis is that the poor performance of low discount factors is caused by large size differences in the action gap across the state space. So what this means is it's not so much the size of your action gap at a particular state that causes trouble, it's the size difference across the state space. Now if this is the correct cause, this means you can correct for it by building a method that has more homogeneous action gaps across the state space for low discount factors. And that's exactly what we did. So you can achieve this by using a logarithmic mapping. So for that, we'll look at this very simple example again. So we have the action gap across the state space of this chain task. And if I now define Q tilde as the logarithm of my regular Q value, and apply this mapping to every Q value, then I can then look at the action gap in the logarithmic space, which looks like this, which makes a lot of sense. If there's an exponential decay of your action gap size in your regular space, if you then map to the logarithmic space, it's constant for any value of the discount factor. Now, this is sort of an idealized case. I picked this task because it resulted in really nice in constant action gaps. But if you look at more general tasks, then you'll see that it's not going to be exact, the action gap across the state space. But if you take a sparse reward task, if you apply this mapping, then it's going to be much more homogeneous, which is what you want. We don't need exact equal, but it needs to be, the size difference needs to be smaller. So the next challenge is to build an algorithm around this mapping. And it's actually highly non-trivial to build an algorithm with convergence guarantees in a general setting based on a logarithmic mapping. But we were able to achieve this. Now, I'm going to show the algorithm, a simplified version of the algorithm for the special case where you have deterministic environments and positive rewards. And then I'll talk about the generalization of that. So we call this algorithm logarithmic Q-learning. And I'm just going to compare it with regular Q-learning. So here you have the regular update rule for Q-learning, and this is the logarithmic update rule. So it's very similar. However, there are now two functions involved. We have f, which is the logarithmic mapping function, and we have f minus 1, which is the inverse of that. Now note that I've added a small value here. This is to be able to represent the value 0. And you can prove for this algorithm that it converges to, that Q tilde converges to f of Q star under standard assumptions. And empirically, you can show that for sparse reward domains, the action gaps are more similar in size. Now, there are two types of generalization required to be able to apply to any task. First one is we want to generalize to negative rewards as well, and we want to generalize to stochastic environments. Now, as it turns out, generalizing to negative rewards is fairly straightforward, so I'm not going to talk about that right now. But I want to talk about how to generalize this to stochastic environments. So first, what's the issue here? Well, the issue is that we're now performing all our sampled updates in the logarithmic space, whereas if you take the expectation of a logarithm, that's not the same as the logarithm of an expectation. It's an underestimate, which is a well-known result, Jensen's inequality. So the consequence of this issue is that if you apply the same update rule that I just showed to a stochastic environment, then Q tilde converges to an underestimate of f of Q star. So it converges to the incorrect value. Now, this seems like a very hard bound, and for a long time we believed this to be a very hard bound that's impossible to get around until we found a way to get around it. And I'm going to show you the modified update rule that is required for that, but first I want to talk about the intuition for the solution. So the intuition is that the step size really conflates two types of averaging over stochastic transitions and averaging over states. And ideally, we want to separate these two and do the averaging over transitions in the regular space and averaging over states in the logarithmic space. Now, you can not do that exactly, disentangle that exactly, but you can do something that has a very similar effect, which is as follows. So you have, this shows the logarithmic Q-learning update rule for deterministic environments, where you take the update target UT, map it to the logarithmic space, and do the averaging there. The modification we made is that we have an in-between step where we do averaging in the regular space, getting U hat, and then U hat is mapped to the logarithmic space, and there a second averaging occurs. So now we have two step sizes, alpha regular for averaging in the regular space, and alpha log for averaging in the logarithmic space. Okay, so let's have a look at, and so for this algorithm, you can prove that it converges to Q star under standard assumptions, plus the assumption that alpha regular goes to 0. Okay, I have to wrap up. I have 0 minutes left, I just saw. So let's go back to that initial problem of the state sequence where you have both positive, negative rewards, you have some stochasticity. So this was the Q-learning performance. This is the performance of logarithmic Q-learning. So what you see now is that we were able to recover the performance for low discount factors. And if you give it more samples, then we convert the optimal Q value for any value of the discount factor. Now, this is a very general principle. You can apply it to, for example, DQN, which is what we did. So this graph here at the top compares log DQN with DQN. And the graphs at the bottom show that we, on average, we do better. One thing I want to mention is, so you might notice that we don't outperform DQN on every game. And the reason for that is that this logarithmic mapping is able to get homogeneous action gaps for sparse rewards domains. But not every Atari game is a sparse rewards domain. But the good news is that you can come up with different mappings that can generalize this to non-sparse rewards domains. But yeah, that's something for future work to look further into. Okay, that's it. Thank you.
We have time for one quick question. So I have one question, which is it seems like this is doing something somewhat the opposite of the Z-learning framework from Emma Todorov. Are you familiar with that framework, and can you comment on the differences?
I'm not fully familiar.
Z-learning. So I believe that if I remember the paper correctly, they actually do Q-learning, but in the exponential space of Q-learning rather than in the logarithmic space.
Yeah. So I think this particular work was really focused on trying to understand why low discount factors perform poorly. So a lot of the work was really focused on figuring out what's the right hypothesis. And it turned out that mapping to a logarithmic space was a possibility. Now, one of the hardest problems for us to solve was getting convergence guarantees. And that's what we actually spent most of our time on. So it's not so hard to get a method that converges, but that it converges to the correct optimal Q value under the particular discount factor. That was one of the challenges. And although I'm not familiar with this work, my guess would be that condition would not hold. It's a non-trivial condition, and we had to work hard to get it. So,
Great, let's thank our speaker again. So next we'll move on to a session of 5 spotlight sessions, and we'll start with Camille.
So we all know that greed is bad, but policy gradient methods are greedy. So specifically, if we think about a continuous banded problem where we were optimizing a policy to maximize this quadratic function, what happens is, as we run our actor-critic, our policy gradient algorithm, the variance becomes smaller and smaller. Another feature of modern policy gradient methods is that they use a lower bound on the critic. So to give you a little bit more background on that, basically when we learn a critic, we use a Bellman-style update. And so what happens is, if the estimate of the Q value on the right-hand side is too large, then the estimate of the Q value on the left-hand side becomes too large as well, and that effect becomes amplified by policy optimization, because what the policy optimization is doing is going in the direction of more Q. And that can mean that our critic value is catastrophically overestimated. So that phenomenon is well known in RL, and the typical fix for now is just to use 2 bootstraps of a critic, and whenever we need a Q value, we just take the minimum of the 2 values. Now, the combination of these 2 things, the fact that policy gradient methods are greedy and the fact that we use a lower bound on a critic, leads to problems. And the first problem is pessimistic underexploration. So the red line in this figure shows this lower bound. And so what happens is when our policy reaches an optimum of the lower bound, the variance becomes small. And so we're not exploring enough, even though in this case we should, because the distance between the red line and the actual true Q value, which we don't know, is large. Another problem is Gaussian policies, and actor-critic methods very often use Gaussian policies. The Gaussian is symmetric around its mean. So we sample in a given direction, we sample with the same probability as the opposite direction. That is basically almost never optimal, because some directions are more interesting than other directions for typical problems. Now, the way we solve these problems is by exploring with an upper bound. So in a modern actor-critic method, we already have 2 estimates of a critic. And now what we do is we use these estimates to estimate 2 quantities, the mean and the standard deviation. And these quantities correspond to an approximation to our epistemic belief about what the Q value is. And then what we do is we write down a UCB-style upper bound, which basically says my upper bound is the mean plus some optimism term plus the standard deviation. And, well, the question is, how do we explore? So when we choose an exploration policy, we want a policy that does 2 things. It has to be close to the target policy, which is what the actor currently believes to be the best policy for the problem. And we also want to maximize this upper bound. And if we write down these things in math, then we get the optimization problem given in this slide. We take one more step. We linearize the upper bound. And because we do that, we are able to obtain a closed form expression for the exploration policy. So just to stress the practical point here, this way of optimistic exploration is super easy to implement. You just take a usual actor-critic method, and then when you explore, rather than exploring with what your actor is telling you, you explore with this formula. And intuitively, what it does is it just shifts the exploration policy in the direction pointed to by the gradient of the upper bound. And we can see that this leads to more efficient exploration, solving these two problems that I've talked about before. We shift away from this previous maximum, avoiding it, we are directionally informed. It works in practice. We improved on soft actor critic despite not tuning hyperparameters on humanoid, which is our hardest task. Qualitatively, what happens is, let me try to play this. Our policy falls down much later than the soft actor critic policy. These are not cherry-picked, so this is basically like any random seed you get this. I got stuck, sorry. The laptop stopped responding, sorry for that. Okay, it's just the last slide, so let me finish. We have openings for interns, postdocs, researchers. Talk to me at the poster session. It's poster 179. Thank you very much.
Okay, hi, I'm David from Uppsala University in Sweden, and I'll be presenting the following work on incorporating robustness into exploration in the context of reinforcement learning on behalf of my former colleague, Jack, who can't be here today. So, in reinforcement learning, agents such as, for example, quadrupeds, robotic manipulators, or virtual actors in video games must explore their environment to learn which actions maximize rewards. However, in many applications, this exploration is essentially random, and agents learn basically by trial and error. In this work, we want agents to do exploration that is robust and targeted. So by robust, we mean that exploratory actions will not destabilize the system, avoiding catastrophic failure. And by targeted, we mean that the exploratory actions will probe the system in such a way that we get information about the environment that helps to solve the specific task at hand. Additionally, it is well known that there typically exists a trade-off in reinforcement learning between exploration, that is, taking actions to extract information, and exploitation, that is, taking actions that maximize reward in the short term. In this work, we actually achieve the optimal trade-off between exploration and exploitation by formulating the search for the policy as a convex program that can be efficiently solved to global optimality. But of course, such a strong result relies on strong assumptions on the system and the environment. So, in particular, in our work, we restrict our attention to linear dynamical systems with perfectly observable states and unobserved disturbances that are normally distributed. Our task is to find a state feedback controller that minimizes a quadratic cost on states and actions. Now, the challenge is that we don't know the parameters and must learn them online while controlling the system. The key quantity in our formulation is the empirical covariance matrix D, comprising states and actions. In the search for a policy, this matrix D shows up in two places. First, in the quadratic cost to be minimized. Here, a smaller D is better as it leads to lower costs. And second, in the variance of the distribution over the unknown parameters. Here, a bigger D is better as it leads to reduced uncertainty in our knowledge of the parameters. So these points clearly illustrate and quantify the exploration-exploitation trade-off in our problem. Now, the search for a policy takes the form of a minimization of our quadratic cost function, subject to a robust stability constraint that ensures, with high probability, that the policy will stabilize the true unknown system. This objective is linear in This objective is linear in our empirical covariance matrix D, and the stability constraint is a linear matrix inequality. So taken together, this gives a convex optimization problem that can be efficiently solved to global optimality. Matrix D is then chosen as to optimally trade off exploration, that is big values of D, and exploitation, that means small values of D. Note that in many recent works, an absolute measure of uncertainty is considered, such as the 2 norm of the parameter error. This collapses all knowledge of the uncertainty into a single scalar dispensing with any structure. In contrast, in our work, we preserve structure in our representation of uncertainty by working with the empirical covariance matrix D. This allows us to optimize the policy for uncertainty reduction in the parameters that matter most for control. So now here on this slide, we see the advantage of a policy which it achieves targeted exploration. We compare the proposed approach to an epsilon greedy policy. On the left, we plot the total cost obtained by each policy. Here, the proposed approach outperforms epsilon greedy and attains a lower cost. On the right, we plot a measure of total uncertainty in the system at the end of the experiment, after the policies have been applied. Here, lower uncertainty is desirable. Now, you see that the proposed approach actually results in higher absolute uncertainty, despite the fact that it achieves better performance as measured by the cost. This suggests that the proposed approach is indeed doing targeted exploration, minimizing uncertainty in the parameters that matter most for control, rather than minimizing uncertainty in an absolute sense. Thank you very much.
Hi, hello everybody. Hi. Yes, so I'll be speaking today about a work, tight regret bounds for model-based RL, with greedy policies. So in short, our work basically shows or establishes that model-based RL with short-term planning has the same performance as model-based with long-term planning. Now, using short-term planning allows us to get a reduced computational complexity by a factor of the state space. And we proved that we actually have the same minimax performance as the full planning counterpart algorithms. Great. So more generally, we have 2 main approaches for reinforcement learning algorithms. We have model-based approach and model-free approach. We now know that the model-based approach is minimax optimal, whereas model-free approach has worse performance by a factor of h, factor of the horizon of the MDP. And this might suggest that model-based RL has better sample complexity than model-free RL. So the natural question is, why not using it? Why not using model-based reinforcement learning? So there are 2 main disadvantages of model-based reinforcement learning. One is its space complexity, because we need to save the transition model, whereas in model-free reinforcement learning, we don't need. The second disadvantage of model-based reinforcement learning is its high computational complexity. So why is the high computational complexity? It's mainly because model-based reinforcement learning in its current form, we need to perform long-term planning, meaning we need to solve MDPs in each iteration, in each episode. And for example, we can observe here we can take a look on a generic model-based RL algorithm. In the beginning of each episode, the algorithm solves an MDP. It acquires its optimal policy, and then it acts according to its policy and gather new experience. And this process is repeated after that. This approach is the common approach in most, in fact, in all previous works. However, in practice, only short-term planning is used in model-based reinforcement learning because it's really computationally heavy to solve MDP at the beginning of each episode. So a natural question which arises is whether short-term planning in model-based RL has the same optimal performance. So in this work, we prove that model-based reinforcement learning with short-term planning is minimax optimal for the tabular case in finite horizon MDPs. Specifically, we analyze a generic model-based reinforcement learning algorithms which uses greedy policies. Instead of solving an MDP, the algorithm explores by using a greedy policy. A greedy policy is, in fact, in order to calculate it, we need to solve a one-step planning problem. So instead of solving MDPs, we merely use one-step planning operations. So to conclude, we proved that model-based RL with short-term planning achieved the same performance bound as model-based RL with long-term planning. This allows us to achieve a reduced computation complexity by the factor of the state space and to achieve the same performance. Lastly, we believe that there's an interesting open question that this work raises. Specifically, if one-step planning is minimax optimal, then how come we need to use look-ahead policies in reinforcement learning? So thank you very much for your attention, and see you at the poster session.
All right. Hi, everyone. I'm really excited to tell you about our recent work on hindsight credit assignment and its work with all of these amazing people that are on the slide. Okay, so the key question that credit assignment asks is, how did my past actions influence the future outcomes that I'm experiencing? And the way that an RL agent usually goes about this question is by relying on these default assumptions about the MDP. And so taking time as the key proxy for credit relevance. So for example, here we have credit assignment in RL, or Carl. And Carl looks at the weather forecast in the morning and has to decide whether or not to take an umbrella to work. Carl decides not to take the umbrella, goes to work, and it ends up raining. So now Carl has to figure out what it was in his day that caused this bad thing to happen. And because Carl is an RL algorithm, he's going to go back through his day in backward chronological order until eventually, after many trials and iterations, going to figure out that it was in fact the umbrella. And what we'd like to happen instead is we'd like to be able to move the credit directly from the rain to the umbrella. And so the key thing that we propose in this paper is to, instead of just relying on these standard assumptions, to try and learn credit relevance explicitly. So what do I mean by that? Here we have some trajectory tau starting from a state x. We propose to consider the probability of a past action having been taken in state x given some function of this future trajectory that in some sense encodes an outcome that we care about. So in the previous example, the action would be whether or not to take the umbrella, and the outcome would be Carl getting rained on, right? And the cool thing about this is that this quantity kind of almost explicitly encodes the credit assignment question itself, right? So let's see how it can actually be helpful. Let's say this trajectory tau went into some state y, but after reaching y, it turned out that there was a more direct path the agent could have taken from x to y. And so perhaps some other action B should be getting more of the credit for y than the action A that the agent happened to sample, right? And that's exactly the kind of relationship that this thing encodes. So then going further, let's say the agent took some action C and ended up in a state Z, but in fact, any action it would have taken would have led to the same state. And so overemphasizing C is just a source of variance. And here we see that conditioning kind of on this future state does not add any extra information about the action. So here in this thing, implicitly, I kind of took the future outcome to be the future state, but it can also be the entire return, which is what we care about ultimately. So it actually turns out that this is not just a heuristic, but we can rewrite our usual value functions using this thing. So for example, here we have our normal discounted sum of rewards, but each reward is now weighted by exactly how relevant the action whose value we're estimating was to achieving the state that is giving us the reward, right? And we can do exactly the same thing for the return. So of course, in practice, we're not going to have these things just given to us, and we have to estimate them from data. And so the family of HCA algorithms essentially breaks up the learning problem into learning this hindsight distribution and then using it to learn value functions or policies or whatever we care about. And here I'm showing two things, but there's kind of a whole space of things that can be considered. We devised a set of diagnostic tasks that illustrate issues with standard credit assignment and show that HCA is able to tackle them effectively. And if you want to know more, come to our poster. Thanks.
So, hello, my name is Adam Geyer. I'm going to be presenting some work I did together with David Ha at Google Brain called Weight-Agnostic Neural Networks. So, all animals are equipped with some special skills from the moment of birth, whether it's the nursing instincts of infant mammals, the swimming abilities of baby ducks, or the capabilities of newly hatched iguanas to recognize and escape from predators. But at the same time, we're beginning to understand that machine learning architectures also have innate abilities. A recent work called Deep Image Prior showed that convolutional neural networks are so well suited to image processing that they're able to perform tasks like super resolution, denoising, and even inpainting without any prior training. So, fascinated by these kind of innate abilities, we wanted to see how far we could push this idea and really see if we can make neural networks that encode innate abilities. So the question this work asks is, to what extent can neural net architectures alone encode solutions to tasks? So this is a different kind of neural architecture search. Rather than looking for neural net architectures that, once trained, perform very well, we're looking for neural net architectures that perform without any training at all. And so to do this, we're going to judge our networks based on their zero-shot performance. So their performance when we just randomly initialize the weights. Now, because the weight space is so large, if we want to get efficient, or we want to efficiently and reliably get an expected value for how well these networks are going to perform, we use a special constraint. And that constraint is to use a single shared weight value for all the connections. This collapses the dimensionality of our weight space down to 1, allowing us to easily sample this. And so whenever we want to judge how well a network works, we just do several rollouts, and each time using a different value. So the algorithm looks kind of like this. So we create an initial population of minimal networks. So these have just inputs, no hidden nodes, connected to some of the outputs. Then we evaluate this population of networks with a range of weight values, shared weight values. So all the weights equal to 2, all the weights equal to -1, etc. And the performance of a network is the sum of all the reward gathered over all rollouts. Then we rank these networks based on their performance and complexity. So given 2 networks with the same performance, we prefer the one with fewer connections. Then we vary these networks to create these top-ranking networks to create a new population and repeat the process. So this is kind of an evolutionary approach. So we can vary our networks in one of 3 ways. We can either insert a new hidden node, we can add a new connection between existing hidden nodes, or we can change the activation function. So We use many activation functions. Some of them could be ReLUs or sigmoids, but also weirder ones like Gaussians and sines. We test this weight-agnostic neural network approach, or WAN, on 3 different reinforcement learning tasks. So we've got the classic cart pull swing up. We have a bipedal walker where you control this little guy and you're rewarded for efficient movement. And we have a car racing from pixels tasks, where we use a pre-trained VAE to compress the pixels down into a latent space that's lower dimensional. And we compared these WAN-found topologies with those from just standard topologies that we found in the literature that when we know when they're trained, they can reach state-of-the-art performance. And we found that if you randomize all the weights of all the networks, then they don't perform that well. But if we use a random shared weight on our weight-agnostic topologies, they actually can produce useful behaviors. And the single best shared weight produces actually pretty good behaviors. So maybe not reaching state-of-the-art, but with this cart pull, after a couple swings, it balances it. We get, with this bipedal walker, we get effective, if inefficient gaits. And with these, with the car driving, we just, maybe it's a little bit wild, cuts some corners, but still completes the race. Critically though, if we actually tune the weights of these networks, they perform the same kind of state-of-the-art performance as our general purpose networks, and are able to do so with topologies that are much, much smaller. So sometimes orders of magnitude smaller. So these encouraging results in reinforcement learning domains made us wonder how far we could actually apply this approach. And so we just sort of for fun, we tested this on MNIST and got a network that looks something like this. And here, if we use just a random weight into this network, we get an expected accuracy of about 82%, which is much higher than chance. And that best single weight gets around 92%, so a little bit better than a linear regression. Of course, if you used a multi-layer CNN, then we aren't going to get nearly as good. But the point of this was never to develop a high-performing classifier. The point was to start the first steps towards a different kind of neural architecture search. A neural architecture search where we're looking for architectures that contain innate biases and priors. So we have our poster tomorrow, and if you want to learn more, please look at our interactive article at weightagnostic.github.io. Thank you.
That concludes this poster session. We now, or this talk session, we now have the poster session.